Megha Pandey, and she is going to speak about quantum securities, expanding to the new era of cybersecurity. Megha, I'm just handing over to the mic, and please share your screen, and we will check it, and you can take it forward.
Yeah, sure.
Yeah, visible?
Mhm. It's visible.
Yes, it's visible.
Great. So I guess we can start.
Yes,
Um,
please
yeah.
proceed. Yeah.
So, my name is Megha, and I am a network engineer at Wipro. I usually work with a lot of bunch of upcoming technology, emerging technologies, and one of my favorite is that quantum computing. Okay, now quantum computing is a vast subject. It has so much to deliver. It's about quantum physics, quantum mathematics, and computer science combination of all of the things, electronics and everything. So as an engineer, when you start with your journey, you know a lot of things about physics, mathematics, related to the algebra. And when you deep dive into this particular stage, you are able to understand what is the need of quantum computers, what is the need of physics in quantum computing. And here is why I present one of the topics like quantum security. Okay. Now, why quantum cybersecurity or quantum security is important into the phase where we are living right now. So everything in this world is on the platform. You search anything, you will get with just one click. Everything is just one click far away from you. So for this, we have to have data which is quite secure. We have to have a place where we can just rely on our secret chips, or we can say secret keys, to communicate with each other when nobody listens to us. Okay. And for these kinds of things, we have created a new era of quantum computing and quantum cybersecurity. Now, a lot of people are not aware of quantum cybersecurity and what quantum is. So throughout the slides, we are going to explain a little bit about what is quantum computing, and then we'll learn a little bit about quantum cybersecurity as well. Okay, so this is kind of a research proposal kind of thing. So basically, related to research and computing as a whole, because it requires, once you understand the basics of quantum security or quantum computing, you will be able to understand the computing part as well. Okay, so that gets over. So once Sundar Pichai said that in a span of 5 to 10 years of time frame, you will be able to break what the encryption that we have made today. And guess what? It was true. You might have heard about Willow, the latest, AI model for quantum computers. So it can produce any kind of, models that you require for your data to be processed. In similar ways, there would be a situation, or there would be a place where we can solve n number of solutions. We can get n number of answers of one single question with the help of quantum computers. Okay. Now, we need to understand what is qubit. A normal system works on bits. It's the classical computers. We will differentiate classical computers as normal computers, and a quantum computer with a qubit. Now, a computer works on bits 0 and 1. But the difference between a quantum computer and a classical computer is that we are able to work on qubits as well. That means 0, 1, and a combination of 0 and 1, which is the superposition. So these binary digits actually help us to, find the value in a machine language. But what happens when we get answer in the point of 0.01 or 0.5. We are not near to the approximation. We know there is a value of pi, 22 by 7 or 3.14. But what if we want we want the real value of pi? With the help of quantum computers, we can get the value. We actually got the value of pi, and but still we don't use it because it's a quite complex. It basically works with the probabilities, the answers of the probabilities. The quantum computer actually knows it pretty well. Now, since we are talking about cyber securities, we know that we have fiber cables and all these kinds of things, but data transmission. Okay, one of the new thing is the photons. Okay, the photons are a kind of sunlight energy which are quite fast. It can propagate or it can send the data in very less minutes or milliseconds, you can say. Just like it's as fast as light. So sending data will not be a big issue for us. And because we're talking about a supercomputer, we really need to have a super transmission chain for our supercomputer. Okay. So for this, we use photons. Now, photons are very fast. They are very useful for data transmission, which are secure because there is one principle of quantum computing, or you can say quantum principle, which does not allow us to clone a simple thing. That means if you want to send one piece to someone, and there is eavesdropper in between. If he or she knows that there is you're trying to send one rupees, the data which is going to be sent or the message which is going to be sent will not be cloned. If it's one cloned with the eavesdropper, the same data will not be sent to the end user. And this is the drastic idea about quantum cyber protocols, or you can say quantum cryptography protocols as a whole. Okay. Now, let's understand a little bit about quantum cryptography with the help of Alice, Bob, and Eve is eavesdropper. Alice and Bob are going to communicate, and they both are quantum engineers. Here, we want to have a very reliable cryptic communication between these two people, and they are trying to use a new technology, which is the quantum technology, through which they are going to communicate with each other. Now, there are n number of things or n number of places, like in defense. We want our communication to be very secure. We don't want any other people to, come in between our communication, or they might be like eavesdropping us. We really don't want that. So for these kinds of technologies are made for these particular places as a whole. With this example, we are going to learn a little bit. Okay. So the private key encryption. Now everybody knows about. If you were in your, like high schools, you must have known about the private key encryption. There is one key which is symmetric and it is sent to the end user, and the end user only has the idea to decrypt it. Just like this lock, only one key, and you can only unlock it. If you have the key, you will be able to unlock it. If you don't have the key, nobody in this whole universe can unlock it. So these kinds of things is a major part of quantum cryptography or quantum protocols. Okay. Quantum key distribution. Now, these quantum computers, we have one property which is called the quantum key distribution. How this key is distributed as a whole. There is non-cloning, like I said, as a non-cloning theorem, you'll not be able to, decode any of the messages, or if you decode any of the messages, the same message will not be cloned. That is, if you have written one, you can't, if there is a eavesdropper in between, if he writes the same value as one, the same value will not be transferred to the end user. or there might be a little bit change in the end user statement, or maybe the end user message, that the message that end user receives. And this is how the person would be able to acknowledge that there was an eavesdropper and there had been some changes in the message, and now I can understand that I have to use a different way of sending my properties or sending my messages. Okay. Now, there are three major protocols as of now, which are used in quantum computing. Okay. And they are very, very amazing protocols. Okay. So the first one is BB84 protocol. Now, those photons, as a whole, photons are very fragile, and once they are used, they can be destroyed easily. And once they are used, they are given to the local system. They are provided to the local system. Only idea is that the end user will be able to delete it, and in between, if the data is damaged or if the data is misled to somewhere, the same data will not be transferred to the end user. That means no copying of the data. Nobody will be in between, will be able to understand the whole message. And if they are able to understand the whole message by any chance, if they are using a smart quantum computer, the same data will not be sent to the end user. And this will create a hassle, and the answer which the end user will be receiving will be very incorrect. So once you verify from the client to the server, or maybe from one end user to the other end user, they will be able to understand, yeah, there was a glitch in it. Okay. So the BB84 protocol is quite easy. As you can see, Alice has given us a value as 1. Okay. She's the first person, and Bob is the second person, and there is Eve. Okay. So what happens? There are two states in which the data is being sent in the polarization filter. Now, photons, they use a polarization filter in which the photon is passing. Okay. These are 4 states. As you can see, plus, minus, and diagonal, and horizontal. Okay. Now, once the photon is transferred, I don't know the state of how the polarization filters is transferring the data. At a certain point, when Eve checks with all of the 4 states, it's quite impossible. Okay. Nobody can check it with all 4 states at the single time, because the photons are quite fast. By any chance, if it checks the correct one, like this is the photon, and the person, okay, let me just use the ink. Okay, now Alice sends this photon with the help of a minus polarization filter. Okay, polarization state, or you can say it's plus, minus, diagonal, and horizontal. Okay, in these way, these are the 4 states. Now, if Alice sends it in the minus state by any chance, and the transmission of photons happen, they move in each and every state. You can see they are moving as a whole until and unless they reach to Bob. But if there is F, and if she tries all of the 4 states as a single time, it's not possible for the first time. If they have a super quantum computer, they will be able to try, and the end result is that she was transferring the 0 state. She received the 0 state, but the same value will not be given to the Bob. As you can see, there is no cloning of the theorem non-cloning is working over here, and the end user that receives the value is 1, which is incorrect. She sends a 0 and Bob receives a 1. So initially, we have found that there was a misglitch, or there was someone hearing to our messages, or maybe they have eavesdropped our message. So this particular BB84 protocol was very helpful because it had all these 4 statements. But initially it was quite difficult for the end user, that means for to filter this particular thing. Okay, he has to know that I have all those 4 states and I have to check to each and every state. And maybe if somebody eavesdrop us, I'll get a fake value. That means an incorrect value, which is not good for him. So there was a change into the protocols, and we are going to learn another protocol here. Okay. Now these are the values that were actually received if the bases were like this. These are diagonal. Okay. It's diagonally sent. It's horizontal. This additional, or this is in a crossroad. Okay. Plus minus. There are multiple states in which the bases can be sent. Now these are bases. Let me just clarify one thing. These are the photons. They have either a 0 or the 1 or maybe a superposition. But the polarization filter are known as the bases. It's plus, minus, and diagonal. Okay. Now there was another filter, another protocol, sorry, which was the non-orthogonal state protocol. Now this protocol only used 2 states because it was quite hard for the end user to understand which state the user has sent the message. They used only 2 particular state, either this one or this one. That means if you are sending a 0-bit data, the encoded value will be in this state only. That means if Alice is sending something to Bob, the 0 value will be only encoded in this way, horizontal way. Okay, and decoded in this way. You can see over here. And if the value is 1, it's going to be in a plus state and in the vertical state as well. Okay. But this particular B92 did not work very efficiently. The reason was that it was not able, the end user or maybe the people who were working on it were not able to understand how easily we can use it. Okay, there might be a problem. There were glitches kind of thing, or maybe you can say you can read a research paper on B92. We were not able to get the correct values of large data. Suppose I'm sending a value of 010101 on a 32-bit. Okay, the whole value is 32-bit. They found glitches and it was quite slow. Okay, so this was demolished and this was not too much popular over here. And then they moved to another protocol, which was E91. Okay, so the 2 successful protocols were BB84 and E91. Okay, now E91 was developed by Arthur Eckert in 1991. So this particular protocol was quite widely used because it uses quantum entanglement. Now, once you got to know what is quantum entanglement, it's quite easy to understand. If I am at one state of the universe and other person is one state of the universe, that means I'm in the North Pole and the other person is on the South Pole. We meet at a particular place in between. Okay, we have 2 boxes. It's box A and box B. Okay, one of the box consists of a ball and another one is empty. We shuffle this box and I once again take a box and I go back to my another place, which is the North Pole, and the other person goes to the South Pole. Now, eventually, when I open that one particular box and I found a ball inside it, I will know that the other person who was in the South Pole will not have anything inside the box. The same person, when he or she opens the box at South Pole and they found that the box is empty, they will know, okay, acha, Megha will have a box which has a ball. So we are connected without a channel, right? We do not have a communication channel over here, but still we are connected. Now, this connection is known as quantum entanglement, the state of getting connected in the universe through any of the reasons. Okay, you are connected with me because you want to learn. Okay, you want to understand what quantum computing is and what quantum cybersecurity is. In the same way, we have a quantum principle of quantum entanglement, which lets you connect with the universe without having a straight channel of communication. And this is how the ECAT E91 protocol is being used. Now, the sender and the receiver, that means the Alice and the Bob, share a quantum entanglement basis. That means bases are either the plus and the minus. Okay. Now, if Alice sends any kind of message to Bob, it can only be decoded in the minus state. If it is not in the minus state, it will not be decoded and received by Bob. Okay. If she sends a message in a plus state, the only answer is the only message will be sent to the end user to Bob if it is in the minus state. Now, eventually, if Eve or an eavesdropper finds out that they are using quantum entanglement to, decrypt this message, he has to know what is the end of all those things. Okay, what are the bases? What is the quantum entanglement state? It's one, and it has to be minus. He has to know everything, or she has to know everything about it. Now, which is not possible because there is a private key encryption which does not allow it to happen. If you know, you can find the answer of only one person. The another person entanglement state will be not known, and this is how they will be able to share data in a different quantum channel without interference of keys. Okay. Now you can read about it. The scheme relies on two properties of entanglement, and that is the synchronization. Okay. The polarization, that means this polar states, plus minus, diagonal, and horizontal. This has to be filtered properly. Either it's this one or this one. It is made by the quantum QDK, quantum distribution key. They can choose anything. Okay, which kind of two states are perfect, and they can sync and they can send the data, which is not even known by Alice as well. वो कहाँ पे and how it's going to be decrypted at the end of the day to the end of Bob. So which is quite secure. And it's easy to use once the even you were able to understand the E91 protocol as a whole, because it was having a state channel where we don't have to use all of the four protocols or maybe all of the polarization states. It's easy. And that's why it's much favorable rather than BB84, BB Qubit. This is how I end this presentation as a whole. And I want to know if you have any questions. I know it's quite hard to understand at a very, initial state, but since it has a lot to deliver and a lot to understand, maybe you can take the slides and you can read later on, to which you will be able to understand what is the communication between, a realistic communication and the virtual communication which happens in the quantum computing. Now you must have watched some movie like Avengers. When you watch those kinds of movies, you know that things are not so much realistic. They're having an action or the planning is quite in a different state. Okay, like वो पास में जा सकते हैं, which is not even possible, right? But still it happens. So this is something kind of unrealistic thing happening, but we are not aware about it. Okay. So it's quite related to research, and I hope you will be able to understand later on if you read a little bit about qubits, quantum computing. Okay,
Thank you so much,
I think
Megha.
that's it.
It's completely new topic and so related to,
I
as
can
you said, the
understand. It's
qubits
quite out
related.
of the box.
Yeah, yeah.
Yeah, it's out of the
Quantum,
box, but
but it's curious, like how it is going to work and all. Thank you so much for sharing
yeah,
this knowledge. Yeah,
thank you.
yeah. Thank you so much, Megha. Thanks for your time. Thank you.